Welcome back to our course on introductory quantum mechanics for computational biologists. So over the last lectures, we performed a sort of an overview. We presented an overview. We discussed an overview of the essential features that contradict our common wisdom we developed in the classical world and in classical mechanics in particular, which become apparent once you investigate matter at a more microscopic scale. So as you approach the quantum realm, you begin to observe phenomena which are exotic from the point of view of classical mechanics, and then cannot be in any way understood by applying basically Maxwell's equations and Newton's law together. Like I said in the last lectures, there have been a number of attempts to sort of make sense of these results within classical mechanics. And after that, there have been a number of attempts to minimally twist quantum mechanics, classical mechanics, in order to include an explanation for this phenomena, basically trying to change in a sort of a minimal way the theoretical framework of classical mechanics in order to account for this phenomena. But all these approaches have failed. And therefore, somewhere in the beginning of the last century, people were unavoidably led to admit that an entirely new theory had to be built more or less from scratch, in order to sort of cope with the undeniable evidence that had emerged from the experiments. And we want today to sort of follow that path, not in an historical way. The goal of this and probably next lecture will be to play a game, to pretend we are scientists confronted with the phenomenology we discussed in the previous lectures, and try to see that based on that phenomenology, we can guess what the main structure of the new physical theory must be. So really, we pretend we go back in time to the beginning of the 20th century. Of course, we have an unfair advantage with respect to the scientists of the time. You already know the answer, and in particular, I have already studied that subject. So what I will be doing is sort of guiding the discussion, knowing the answer. However, I'd like this to emerge from a little bit of a simulation how science works based on evidence and try to build a new theory rather than just going on the blackboard or the whiteboard in this case and just say, okay, let me present you the new theory. This is the Schrödinger equations. Because I think it would be very mysterious for you to understand where this equation comes from. But let me be very clear from the outset. There is no way you can explain or demonstrate a fundamental physics equation. We had this discussion already in the past. We can only postulate. There's no way you can understand Maxwell's law. They are what they are. They are the results of making, their mathematical expression that summarize a countless number of experiments coherently pointing towards those equations. So even though we will play the game of demonstrating or deriving Schrödinger's equation and other physical aspects in the upcoming lecture, it is important for us to keep in mind that this is not at all any proof. This is just a way of sort of train ourselves to physics reasoning. But ultimately, an equation is just what it is. You could simply come up and say, let me guess this equation with this interpretation and see whether it agrees with the experiment. And if it does, Whatever you say before has no meaning whatsoever. And at the same time, no matter what you say before stating an equation, you'll never be able to prove it, because only experiments ultimately can determine whether it's true or wrong. Okay, after this long premise, let me summarize some of the main features we want to account for. So one of the things that we have sort of cleared in the discussion of the double slit problem, so let me say from the double slit experiment, double slit experiment, one thing that we have sort of taken home is that particle propagation occurs or displays wave-like features. And the second important conclusion we drew from the discussion of the double slit experiment was the particle detection displays particle-like features. So let me remind you where these two statements come from. Well, if you remember, we had a gun, an electron gun, shooting a beam of electrons which impacted walls. And an important point was the emergence of interference pattern in the probability of hitting the hole in this size, which the final board here, which clearly was stating that the probability of hitting the wall in a particular point z of height, or maybe x and y, if you also have spherical holes, here we're only concerned with one dimension, cannot be in any way viewed as the incoherent sum of the probability of going through each of the particles of the wall's holes independently. So this idea that the particle goes through either one hole or the other hole, and in a ballistic manner, and then depending on that, impacts the final wall, is not supported by experiment. Somehow there is interference. Which is a typically wave-like phenomenon, which we interpreted as saying the passage through either hole is not disjoint. It does not provide two disjoint events in the language of probability. So this was something to be reckoned with. So the propagation of the particle from this point to the final board obeys or displays some wave-like properties. However, when you put an array of detectors here, like you cover this board with detectors, you can record exactly the time at which they are hit by an electron, because at that moment they emit an impulse, an electromagnetic impulse, actually a current. And therefore you can place very carefully in space and in time when a particle hits the board. And since you hear isolated, very defined impulses like tick, like what you know familiar with the noise of a Geiger detector for sci-fi movies on radioactivity, when radioactivity is involved, you hear like ta 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 ta, this kind of intermediate sound. Each of these little sounds are corresponding to, in this case, I guess, products of beta decay particle hitting at a particular time your detector. And this is what I mean by particle detection has a particle-like behavior, because that's what particles do. They hit the time, they hit the screen at a given time and place. Now, this combination of things, the impossibility of determining whether you're going through each of the two holes, but the possibility of knowing exactly where you hit the hole at what time, can be summarized in a kind of a suggestive manner by the following sentence. The notion of particle trajectory is untenable. What do I mean by that? Well, what is a trajectory? If you think about it, this is a trajectory. Is a collection of points configured in phase space with momentum and position for different times. Now, if you can really do that, then you really are able to pin down through which hole you went through. But it appears that you cannot do that, which, stated differently, you can think about that, rephrase that very sentence by saying, even though I know exactly the position of my electron at some time, for example, the time where it hits one specific point of the board, I cannot know what was his momentum while impacting the board. Because if I knew, for instance, it could have been this momentum, demonstrating that the particle came from this hole, or could have been this momentum. So you cannot specify both position and momentum at a given time when you perform a measurement on the electron. In this case, we have specified only positions. So this information cannot be attained. Only this information here can be attained. Likewise, there are examples of experiments where you can specify momentum very clearly, but not position. So this can be summarized with the notion of uncertainty principle, which says we cannot determine, or let's be a little bit less colloquial, it is impossible to determine with arbitrary precision the position and momentum of a particle. So in other words, we cannot get a full classical state definition. This is the definition of a classical state, remember from our discussion in classical mechanics and Hamiltonian dynamics. So what this uncertainty principle is telling me, forget about that definition of physical states, because you cannot measure it. So classical mechanics is kaput, because the very heart of classical mechanics, the notion of a state of a classical system, cannot be determined when the particle gets too microscopic for classical laws to break down. You can determine it for bullets or even smaller objects which still obey classical physics, but when you enter the regimes classic of quantum realm, then you have to give up this notion of state. That's the main essence of this work. And let me just remind you that this is not the only uncertainty we have encountered so far. We have encountered also an uncertainty concerning the different components of the magnetic moments of subatomic particle, for instance, the electron, when we discussed the Stenger-Lat experiment. And remember, when we were trying, well, we noticed first of all that magnetic moment was quantized, but this was not even the most surprising fact. The most surprising fact, at least to the eyes of many, including myself, was the fact that, when you have no knowledge of what is the the magnetic moment of the electron should be, then you expect a 50% probability of finding the right and the left. And that's exactly what you observe in the first umbrella. Then when you measure the X component, in order to determine both the Z component and the X component, you get a 50%. And then now you have polarized both the Z and the X, and you would expect to be able now to double check that you've done things right and remeasure again the Z component and find exactly one beam, because you have already determined that they are all spin-ups, all pointing up. And instead, what you find is, again, you have a 50% splitting. So you can never know at the same time more than one component of the magnetic moment of the electron. That's another example of uncertainty principle we discussed. So you can never know both the position and momentum of the particle, nor more than one component of the magnetic moment. I want to emphasize something we said many times in the previous lectures, but it's important to stress them here. This has nothing to do with our technological limitations or to the poor experimental setup we can rely. This is not a technical limitation. This is an ontological limitation. It's just impossible to measure nature. Something in nature cannot be, it's like a sacred principle of nature that cannot be beaten, no matter what you do. And you can think physicists try very hard to challenge these ideas of uncertainty and try to, come up to unlogical conclusion that would follow up from uncertainty and try to see whether they could lead to predictions that could be violated by experiments, but no way. This idea of uncertainty has survived 100 years of investigations and become a fundamental cornerstone of quantum mechanics. When discussing the double slit experiment, we also encountered something totally unexpected. Something more was totally unexpected. We imagined to place a device here, like we call it a lamp. Of course, it's not just a lamp, that was able to flash a light whenever an electron was passing by. So this was an attempt to show that, look, I can actually perform an experiment that is able to determine both the position, because I have recorded the electron in place, and the momentum of the particle. And when you were doing this, all the wave-like behavior of the particle would disappear. Whenever you are reconstructing the particle flashing from one hole or the other hole, then all the wave behavior on this side of the screen will disappear. And again, this is showing you for the second time, in addition to the Stenger discussion, that nature is doing things in some kind of a nasty, pervert way, meaning the act of measuring the system influences the nature of the system, the real essence of the system being investigated. Is it a particle or is it a wave? Depends on what measurement I do. And this is, of course, something completely outside the logical thinking of classical mechanics, because something classical mechanics is either a particle or it is a wave. But again, this has to do with the fact that there's some interference, some non-trivial entanglement between the act of measuring and the intrinsic dynamics of a system. And we sort of waved our hands in saying, it's like trying to measure the location of a ping pong ball by throwing another ping pong ball in the dark and recording the noise. When you hit it, you might know where, you might be able to reconstruct where the particle were, but in this analog experiments, not in the quantum mechanics, you're no longer able to tell where the particle is gone. I mean, again, classical mechanics doesn't have a real observability principle, so you can make the probe lighter and lighter so that eventually you hit it so lightly that you don't perturb its state. But in quantum mechanics, you cannot do that because ultimately you're going to hit a subatomic particle with another subatomic particle, and they are going to be comparable in scales. So the act of probing a system, for example, sending electrons or photons into the system, will change the state of the system because the system is made by identical comparable size particles, comparably light particles. When this happens, then you're, in an uncertainty region. Okay, so what we're going to do now is to try to make sense of the double slit experiments in mathematics. And say, fine, what the double slit experiment tells us is that the probability of finding the electron at point Z is not a sum of the probability of going through the holes, but rather, like waves, is the sum of amplitudes, which are complex functions and then taking the square, the model square. So the first piece of information, we know this is true for waves. And the first things we are led to think, well, maybe that's the same rule. There exists something like an equivalent of an amplitude of the wave that describes how the electron propagates through space until it hits the wall. And these waves basically describe only the propagation and the probability of performing a measurement and finding the electron in a given place at a given time. So that's the first thing we want to buy from this experiment. Basically, by the analogy of how waves behave, reconstruct a good educated guess how quantum particles should behave in their propagation. But maybe, so the idea here is to assume, to throw down a principle that tells us how to compute the probability of finding a particle in a given place. And let me be more specific. Let's say the probability of finding a particle in a given place and time, I'm being more generic here. And, to relate that to an object called the amplitude. And for a two-well experiment, you can think of this amplitude as being the sum of independent waves going through different holes. So that's how waves behave. And we want to do the same for particles because we've seen interference patterns that are proper by wave. Okay. And how do we call this object psi? Well, since they behave like wave, let's call them the wave functions. And now the big question, of course, is how do we compute the wave functions? How do we compute a wave function? Okay, this is what we want to discuss today in this lecture. We try to guess, based on the experimental evidence that I described to you, an equation for the wave function. So what do we want this wave function to describe? Well, first of all, we want to describe wave propagation. So essentially, what we need to find is an equation for the wave function. And again, this is no proof. It's just an educated guess. And I'm trying to educate you through the guess, to formulate a guess and come together. Although we are in a synchronous mode and the notion of together is a little bit generalized in the era of COVID lecturing. But when I was performing these lectures in person with the students, I was really trying to get the students involved in guessing in an educated way what the equation should be. So we want an equation for the wave function. And we want this equation to account for the properties that I've studied. And remember that once I detect the particle's properties are detected are those of a particle. So for instance, the energy of a free electron impacting the screen should be, since there is no interaction, it's just kinetic energy, this should be p squared times the mass of the electron. We should obey this general rule, because that's what a particle will do once it hits the screen, right? So we want to combine this idea of particle and wave. Okay, what's our first guess? We want to find an equation of something that propagates with a wave. Let's find what the wave do and apply the concept of wave equation to our system. Let me repeat this. The first guess is find out what equation do waves generally obey, and use it to compute the wave function. Now, once we establish that the probability is computed from a function we call the wave function, and this has interference pattern, then we look in the literature and say, what the hell do waves do normally? And let's copy that. That's the simplest possible way, and guess. And sorry, no, this is a guess. So fine, let's do that. In order to do that, the first question we need to ask ourselves is, okay, what is a wave? We spoke about that, but we never really defined a wave. A propagating wave. Well, most generally, a wave is anything that depends on position and time, but not in any matter, but in a specific form of a combination of two form functions. So a function that depends, a function is called propagating like a wave, propagating wave, if the position at time t depends on time and position, if the function f depends on time t and position x, not in any way. For example, are cosine of x squared divided by t. But in the form that is, it depends on these two variables through this, either of these two specific combination, and in general, a linear combination of them. Okay. It must be mysterious, right? What does it mean? But let's look at this in particular, and then we look at the other. Well, this first expression is, if I look at the function at time t, maybe it's like something like this. Fn at time x and maybe t naught, the initial time. What this equation is telling me is that if I look at the position of the same function after some time t minus t naught, what I find is exactly the same shape, but translated forward by an amount v dot t. Now in one dimension, there is no vector here, right? So I'm gonna call it v dot t. You see, because at time 0, I have f of time t equals 0, I have f of forward x, and at time t greater than 0, I get the same function, but not evaluated at x, evaluated. So basically the function at this new position, the value of the function in this new position will equal the value of the function of x. In other words, the same shape is translated forward in time as time goes by. And that is, of course, reminiscent of what we expect a wave to be doing. Think about the front wave of a tsunami approaching, is more or less the same shape moving forward. In that case, the function f is the altitude or the amplitude of the wave, based is like forward propagating motion. Likewise, the second term describes a backward propagation. And in fact, if you're sitting on the beach and looking how things behave on the beach, I think have a summer day to spend. You're relaxing on the beach and you see this incoming wave coming to the shore, bouncing to the end of the shore, coming back, and maybe adding to another wave that comes from the other side. And what you see is that the total function, the total amplitude is this algebraic sum of these two waves. Maybe one is going down, the other is coming up, and then they cancel each other, or they're both high at the same time. You get a big bulb going up. So the wave attitude is the sum of these two components, one moving forward and the other moving backwards. So that's what a wave is like in wave theory, propagating wave. Then there are steady waves, and these are how your microwave works. But let's not go too much into the general formalism of wave. After all, we are interested to understand how quantum mechanical matter propagates. So, okay, we got the first question covered. We know we have a good working definition of wave. Is a function of space and time that depends on space and time according to this specific, any of these two combination or a linear combination of these two. And v is called the wave vector. In this case, the wave velocity, and it can be related to the wave vector. An electromagnetic wave is the same. For instance, the electromagnetic field. If you have some, one way to remind yourself of what the electromagnetic field is, well, it's the real part of some amplitudes, time of phase, and that's a planar wave. And again, you see, you can, components by component, you can trace back. This is called K, this is called X. You get the same combination. Now you can pull off this factor here in front and get T minus. You get So basically, we have seen that, the concept of, well, it could be like x component. So you see, this is what people have found over and over in the literature, and the same concept of propagating wave describes both electromagnetic wave or hydrodynamic waves or acoustic waves or spring oscillations leading to wave propagating on a string, and so on and so forth. So the question we would like to ask is, what kind of equation is obeyed by f bigger propagating and f propagating forward and backwards, by the two functions f bigger and f smaller that describe the forward and backward propagating part of the wave. And let me not try to be too much pedantic, but let me just throw out the answer, and let me do it in 1D, and later we generalize to more dimension. But let me make a note, an observation. If I have a function time bigger, which depends on time and space in one dimension through this specific combination, maybe let me say x minus bt. Let me take the second derivative with respect to x of this function. Well, you have to apply the so-called chain rule for differentiation. So let me say this function depends on x and t. I have to use the symbol of partial differentiations because I have more than one variable. And if I take the second derivative, well, let's do it stepwise. I get the first derivative. And when I use the first derivative, I get a minus b. And then, so what is the f prime is the derivative of f bigger with respect of its argument, let's call it z. And then I have to differentiate the argument with respect to t. So I've done d by dz of f bigger times dz by dt. Z is x minus negative t. So this part here is what I call f prime, because if a function of z, this function has only one variable, z. Then I discover that z is actually a combination of two variables, and this shows up in the second term here. So let's take the second derivative, and the second derivative will be, I will drop one second the double prime of z of x minus v and t. But I will drop a factor v squared, and I will get another minus 1 squared. So altogether, I will get that the second derivative with respect to x of this function is actually v squared, the velocity of the wave, times the function itself, that differentiated twice with respect of its argument. So once again, what this means is consider the function f of v as a function of a single variable z. And then, of course, since it's a function of a single variable, of a single argument, anytime I take a derivative, I can put a prime here, because I don't need to use partial derivative symbols if the function is a function of a single variable. And so this is, if you want, it's the same as saying second derivative with respect to z, but there's only z as an argument of this function. Okay. Now let me now take the second derivative with respect to z with respect to x. We differentiated twice with respect to time. Let's now the exercise of differentiating twice with respect to position. Now this time, I have to do exactly the same thing. First, I have to differentiate with respect to the argument z, and then differentiate the argument with respect to x. But now, you should notice that dz divided by dx is v by dx of x minus vt, and that's just vx divided by dx, which is 1. So this is simpler. So it doesn't take much to convince yourself that if you do it twice, you get simply v double prime as a function of x minus t. Okay. So we came to the conclusion that the forward propagating waves obey this very specific differential equation. Taking the second derivative with respect to x gives you the same result as taking the second derivative with respect to time and divide out the contribution of the square velocity. And I want to emphasize that this specific equation follows from the fact that x and t are not completely independent. They are linked together by the definition of the z, which is x minus v per t, v times t. So basically, only if you have a wave, this is satisfied. But again, I want also to emphasize that since we have used I want to emphasize also one more point, that since this equation involves twice taking the derivative, and at the most, any time you take a derivative, you get a negative. Either if you have a minus signs, x minus vt, forward propagating wave, you get twice a minus sign, which will cancel out. While if you had a backward propagating wave, you wouldn't have any of those minus signs. So all this to be saying that the same equation is obeyed also by the backward propagating wave. So that's what is a wave. Okay. So is this the right equation? Is this equation obeyed by electron? That's the question we want to address. Of course, the ultimate answer is ask the experimentalists. Make a prediction for the electron propagation based on this and see if the experimentalists agree or not. But of course, we cannot just do this in this lecture and think about the way to validating this equation per se. But we can see if it's consistent with things that we know to be true in experiment about the electrons, even at the quantum mechanical level. One thing that turns out to be always true, in even the quantum mechanical level, is that the kinetic energy of a particle has the same expression as in quantum mechanics, in classical mechanics. Now you can actually use the detectors that I was telling you about to detect the energy of the particle, because the energy of the particle is entirely transmitted in the energy of the current that they produce. So you have a wave of, these are called calorimeters. Basically, you're able to detect the total kinetic energy of the particle impact. And, by using calorimeters, knowing the mass of the electron, in principle, you can show that that a wave sorry, the electron's kinetic energy is still the same expression in classical mechanics. Let me state it as a fact. Let's call it fact number 1. And let's now, state the fact number 2 that we already saw in the case of the photoelectric effect. And the state number 2 says that for any quantum mechanical particle, the energy of the particle is actually related to the frequency of the wave that describes it. So I would say h bar omega. That's fact number 2. We learned that for photons, and we would like to, generalize this to any quantum particle. If this quantum particle is described by a wave, then if the photon is a quantum mechanical particle, so very likely is the electron. So let's assume, and let's give it for a fact, which has been verified experimentally, that the kinetic energy, the energy of the photon is also proportional to the frequency. So now let's take the simplest possible way to describe an electron. And let's assume an electron is well described by a plane wave. So what is a plane wave? Well, no matter what you do, when you have a wave source, for instance, you put, an electron through a gun, you will generate wavefronts that are like this. We're all familiar with that. However, so these waves are, more or less circular or have their shape. However, if I am looking at these waves from a very small man perspective, my entire size of my experiment covers maybe just a tiny little bit of this wave. What I'm going to be detecting, if I zoom out at this scale, I'm going to zoom this, the red dot there is my board where I detect the electron, and the waves are seen. I will not be able to, detect the curvature of the wave. For all practical purposes, as far as my detection is concerned, everything goes if the wave was an infinite wave front propagating. Who cares if this front ultimately shows some curvature? Just as much as when I'm in the proximity of Earth, I can use a theory, simplified theory of gravitation, which the gravitational force is constant and pointing downwards. And we know this cannot be true because the Earth is spherical. But as long as I'm close and I'm looking at distances that are small compared to the size of the Earth, I will not be able to detect Earth curvature, as Earth flatters very much know. The believers on the Earth, flat Earth, they very much know. And therefore, given this, I will not be able to detect any curvature, and I can make this approximation. Very much so, it's convenient for wave to imagine, to describe theoretically my system, my propagating wave, by saying, okay, my wave could be something like, suppose we have a forward propagating electron for a moment. And let's say, okay, I will have a frequency scale. And then if x is the propagation, the direction of propagation, I will have my velocity times x. Now, you might, sorry, not velocity here, I will call this k, or wave vector times x. I mean, this looks slightly different from the expression v times t equals minus x, but you can pull off from here, you multiply things, right? and you multiply this by k, and you call this omega, and you get back this equation. Right? So although this expression looks slightly different from the one that I discussed before, it is clear that so it looks slightly different from this. Nevertheless, I could have started from this expression altogether from the very beginning and identified each term and show that this expression does describe indeed a propagating wave. Right. Because it's a matter of pulling out a factor and getting some answer. So this is as good as a propagating wave it is as the other expression that I gave. Now, first of all, we can rewrite this expression in the following way. The thing that I did here was actually to recognize that the frequency of my wave is nothing but the energy times h bar. I was using fact number 2. Now, let's look at this quantity k. Well, if I pull out this factor h bar, let me rewrite this in the following way. Well, this is something that we need to understand what it is. Let's call it C. But dimension, since this is a dimension of time, this is a dimension of energy. This combination has the dimension of energy times time, which I rewrite. Remember, the energy is a mass times a velocity squared, so length divided by time squared times time. So this has the dimension of a mass times length squared times to the minus 2. So by analogy, the quantity psi has a dimension that is, this product must have the same dimension as this product. So the length coming from x times the dimension of c must be mass length squared times to the minus 2. Now, because of dimension uniformity, which means essentially that I can trace out the dimension of Xi. The dimension of Xi is basically given by the mass, and then I have a length, and then I have a time. To the minus 1. Right? So this is the dimension of a mass times a velocity. And we know something fundamental that has a dimension of mass and velocity. It's called the momentum. So rather than using the psi symbol, we might as well use the momentum symbol. Okay, so it is tempting to say that the waves with the electron. So, what we're doing is that, okay, we know that the electron has a wave-like behavior. So we can imagine that our setup is small enough so that we can think that whatever wave is coming, it can be approximated with a plane wave. That we wrote a general expression for a propagating plane wave. It looks slightly different from the one we use, but we understand the difference is just in how we use the coefficients in front. But the basic main thing is that you have something depending on time and something depending on x, and then you sum them. So this is in fact a wave. And then, it is very tempting to say the wave function obeys the same equation as the electromagnetic wave. Like photons. Photons are quantum mechanical particles. They obey a standard wave equation because Maxwell's equation described the propagation of photon of electromagnetic radiation through a wave equation exactly of the same type that I discussed before, where the velocity of the wave is, guess what, the velocity of light. So why don't we do the same and see what happens if I apply the wave equation that we just discovered to this equation. So if I assume that P is actually the physical momentum, then I know the velocity of the wave should be P divided by mass. So what happens if I take the double derivative with respect to time, divide by P squared m squared, which is essentially 1 over P squared, and then take the derivative with respect to x squared of my function psi. What this is equal to? Let's make a prediction based on assuming that the wave function psi obeys the same wave equation as the photons, the standard wave equation. Well, if you do, it's very simple to get an answer. So just erase the wrong thing, but let me say I over h bar omega t negative p dot x, right? So let's take the second derivative with respect to time. Oh, sorry, this is h. The second derivative with respect to time is going to give me let's do it. First derivative with respect to time will give me I over h bar e and then psi. This is psi. And the second derivative with respect to time will give me -1, which is I squared over h bar squared. I will drop an additional e squared and then psi. Let's now compute the second derivative with respect, but this is the first derivative with respect to time. Let's compute now the second derivative with respect to space. So I will get the derivative of the derivative. So what do we got? What do we get? Well, this is going to be d by dx. And then the derivative with respect to space would be I over h bar negative of d times psi. I'm dropping the factor p here. And then when I do, that's already there. When I act on the second, I will get again I to the square, -1, minus 1 to the square, 1. So I get -1, h bar squared, p squared. Now, from this equation, we come to the conclusion that the energy of the electron is square is proportional to the momentum square. But this contradicts fact number 1, which we assume to know that the energy by itself was proportional to the square of the momentum. And in fact, this is actually true for photons. The energy is actually C times E for photons. But for electrons, we know the energy is proportional to the square of the momentum. This is called the dispersion law for the electron. So clearly, fact number 1 and fact number 2, that is the electron, the energy is proportional to the frequency, and the wave equation cannot be altogether true. You know, our initial guess was not right. So why going through a wrong theoretical result? Because maybe we're going to use the failure to instruct ourselves and get the right answer. We cannot just believe, you know, some of these assumptions that we've made must be twisted in order for all of them to be consistent. And we assume that this is coming from experiment, and we assume that this is also coming from an experiment. So what we left to do is to modify this equation. Maybe there's another equation which has the following property. It has wave solutions, yet it is consistent with factor number 1 and fact number 2. So in the next lecture, we're going to revisit this failure and try to see whether we can use it, capitalize on what's going wrong to write a new equation that is still has waves as solution, which describe the amplitude from which we can compute the probability of observing the electron, yet does not violate what we give from granted, being the dispersion relationship E is proportional to P squared, and the fact that the energy of a particle is proportional to the frequency of the waves that describes. And the result, as we shall see, will look like the Schrödinger equation. But that's food for another menu. See you next lecture.